This video, we're going to talk about vertical asymptotes of rational functions. A vertical asymptote happens when there's a zero in the denominator that's not a zero of the numerator. As well, when we get zeros in the numerator and denominator for the same number, that's going to give us what we call a hole or a removable discontinuity if you're in calculus. So if you hear anybody say removable discontinuity, they're talking about a hole in a rational function, usually. Not always, but that's the main type of removable discontinuity. So let's go ahead and let's look at 11. And let's look at this denominator, x minus 5. We're going to set it equal to 0 this time instead of saying it's not equal to 0. And we're going to get an equation of a line here when we solve for x. That's going to be x is equal to 5. And that is the equation of our vertical asymptote, since 5 does not make the numerator equal to 0. Let's look at number 12. X minus 4, x minus 2, right? And we're going to have two different equations here. X minus 4 equals 0. Since these are really not equal to equations, there's going to be an and, not an or here, but we'll just deal with it with a comma for right now. And these are boundaries that your function is going to approach but not touch. You'll represent them with a dashed line on your graph when you graph them. We'll be graphing in another video or two. So my vertical asymptotes are at x equals 4 and x equals 2. At number 13 now, x squared minus 4. Again, be making sure every time that you don't get something in the denominator that's a factor of the numerator as well. X plus 9 is not going to cancel out with x plus 2 or x minus 2, so we're good. X plus 2 equals 0. X minus 2 equals 0. X equals a negative 2. X equals a positive 2. That was number 13. Now, number 14, we had one like this in our last video when we have a sum of squares in the denominator that's not going to factor. So we try and set equal to 0. We're not going to get an answer for that, right? No way I can square a number and get a negative. So in this case, there's no vertical asymptotes. If the denominator can never be 0, there's not going to be a vertical asymptote. Let's try number 15. There's my two vertical asymptotes. Neither of them make the numerator equal to 0, so there's no holes. Let's try number 16 now. We have a greatest common factor here of x. X squared plus 9 is never equal to 0 for the same reason that x squared plus 49 wasn't equal to 0 just a couple minutes ago. So my only vertical asymptote here would be at x equals 0, but wait a second, x equals 0 is going to make the numerator equal to 0 because I have a factor of x up there. So this is going to be a whole, not a vertical asymptote. So there are no vertical asymptotes here in number 16. Let me show you 16 another way. So let's try and get it completely factored before we answer the question. Like so. And then I would remove that common factor, but I would keep over here off to the side my restricted domain that x can't be equal to 0 because I'm still not allowed to divide by 0. My new rational function looks like this, and I'm only worried about zeros from the denominator now that we're not zeros to the numerator, and there are none, so there are no vertical asymptotes. Moving forward, I'm probably going to be factoring numerator and denominator like that for every problem, just to make sure that nothing is going to cancel. So that was number 16. Let's try number 17. We factor the denominator here. We have one factor is positive and the other is negative. Factors of 48 that have a difference of 8 are 12 and 4. Like so. No common factors there. So x plus 12, we're going to set equal to 0. X minus 4, we're going to set equal to 0. We're going to solve. And there's our vertical asymptotes. Remember, again, a vertical asymptote is an x equals equation. You have to have an equation of a line. So it has to say x equals the number. It's not sufficient just to say the vertical asymptotes are negative 12 and 4. Now let's look at number 18. We need a positive and a negative. And this is going to be a negative 7 and a positive 1. Gives me negative 7 plus 3 is a negative 4. No common factors there. So there's my two vertical asymptotes. Now let's look at number 19. This is going to be x times x minus 1, 6x, 6x. And this is going to be 11 and 1. 66 plus 6 is 72. Nothing in common here. So there's my two vertical asymptotes for number 19. We're back to a difference of cubes for number 20. No common factors. And this one's not ever equal to 0 in the real world. Graph that in your calculator if you're unsure about it, but it's going to stay above the x-axis the entire time. So there's my only vertical asymptote for this problem. Let's try number 21 now. I don't like that my x is written first here and second here, so I'm going to factor out this -1 before I get started. And that changes the signs of everything in the denominator. I'm just going to be clear and write it as a factor in the numerator. Now I'm going to factor out my common factor of x. And this is the difference of squares. And oh, look at that. There's a common factor there that makes this a -1 over x times x plus 7, as long as x is not equal to a +7. So looking at my denominator now, I have vertical asymptotes at x equals 0 and x equals -7 if I would set each of those factors equal to 0 and solve. Last question for this video. Again, I don't like that negative in front of that x squared, so I'm going to factor it out. It's an x plus 4 and an x minus 4 in the numerator. And then the denominator is an x plus 1 times an x plus 4. Those make a whole and leave me with this. I'm going to set that denominator equal to 0, and I get a vertical asymptote at x equals -1. Come back next time and we'll talk about horizontal asymptotes and maybe some oblique asymptotes. See you next time.